Good morning. Well, I am here, but I'm a little bit behind. So as I was walking in with my son, who was also late, he said that nobody cared if I was late since I was the teacher. And I said, well, that's not really true, so I don't think I can look at it that way, but those were his thoughts.
Jamie, are you still having your final according to the schedule?
Yes, it'll be according to the schedule during finals week. That's correct.
Okay, cool.
I'll put those dates back up here in times, and I'll also be emailing those out to you just to make sure that everybody's clear on what's what. I'll get them. They'll be posted on your D2L site. Actually, they're already posted there, so you may have noticed those there as well. Let me get organized here just 1 second. I'm sorry. And then we'll return tests here in just 1 second, okay? So let me go ahead and put, I'll go ahead and put the dates up here, and that way if you're not sure what those are, or times for the final, you'll have those up on the screen, and you can be jotting those down while I pass back the test real quick, because I want to make sure that we know what's going on with that as well. So let's see here. We have the My Math Lab quizzes. Don't forget about those, okay? So today we're going to talk a little bit about wrapping up the rest of this semester here, because we are at the end. The My Math Lab quizzes 1 through 11. Okay, 11's on chapter 14. You may not have seen that one yet. Go ahead.
On the online, it shows like your total average. Like say, if you.
Can you say that so they can hear also, please?
Yeah, online it shows your total average, but aren't you just taking the highest scores? Because it's taking, like, if you took one and another and it's taking those average, would you just take the highest?
Right, I'm going to take the highest score for each quiz. You can do them multiple times, but if it's not already set like that, I thought I already had it set like that, but I'll double check it. It should be taking the highest score that you get on those My Math Lab quizzes, and between those highest scores you get on the 11 quizzes, as well as your unit circle quiz and your chapter 7 homework, remember the chapter 7 homework thing and the unit circle quiz, those grades are already posted for you on D2L, but those will combine in with those, and I will let one of those things go, okay? So I'll drop one out of either the 11 quizzes or the chapter 7 homework or the unit circle quiz, okay? So, but all the My Math Lab quizzes, they will cut off at 11:59 p.m. on December 7th, which is just right before finals week. That's a Sunday night, okay, before finals week begins. So that should give everybody plenty of time. The exception to that would be if you are just now starting, yes, you can get that done. It's going to be a little more difficult, I think, for you at this point, and there are a few of you on that route, but you can still do that, okay? I highly recommend you do these, though, okay? Doing this not only will help you as you start to review, but it also should be helpful grade-wise, because this average between these and those other two assignments I mentioned counts as one test grade, okay? So this can be what you want it to be, what you make it to be. In other words, there's no excuses about this one, right? So, okay. Any questions about the My Math Lab quizzes? That's the first order of business. Don't forget them. Hopefully nobody's forgotten them. Okay. Coming up next week on Tuesday. So here's where we are more immediately. On Tuesday, December 2nd, I'm giving you a chance to retake one of your tests that day. Okay. Retake day, we'll call it. So on Tuesday in class, that's what we'll do. We'll take a retake test. unless you don't want to retake a test, and that's totally up to you. If you do not show up Tuesday, I'm assuming you don't want to take a retake test. No problem. If you do come Tuesday and take one, I'm making it no risk, okay? I'll take the highest grade. In case somebody does do worse than they did before, I'll take your higher grade of the two, okay? But if you want to retake a test, Tuesday's the day to come do it. So today, since I didn't have the roll sheet back there, as I pass around the roll sheet here at least, I want you people in class with me here to put down which test you think you might retake. In other words, out from your name, put either 1, 2, or 3. I'm not going to pass this until after I pass back test 3, okay? So you can take a minute and look at that. But when I do pass this around, please put 1, 2, or 3. If you put nothing, I'm saying, they're not planning to come. This is not set in stone. If you change your mind, that's okay. I'll have some extras with me, but this gives me an idea of what to plan for. Over in Kingsport, if you all wouldn't care to just shoot me an email telling me which one you're thinking of taking, okay? That work? Just sometime, over the next few days. All right, great. And that way I'll know. Well, I guess I'll get that. Let's see, when will I get that roll sheet back? They could do the same, right? I'll get it tomorrow.
Either that or I could fax it to you. Both.
All right, yeah, that's fine. Why don't you just do that? If you don't mind to fax it to me, that'd be great. And
okay.
That way,
yeah, but I mean, otherwise you'd get it tomorrow for the regular purge system. But I can.
Either way is fine. I didn't know if they'd be running over there tomorrow or not because since there's no classes, I wasn't sure.
Yeah, I think Rob Nelson's coming in the morning to pick up some stuff and take over there. Yeah.
Okay, thanks, Rob.
Yeah,
I got you there. Thanks, Rob.
Okay.
Okay, well, that's fine. So if y'all just want to jot down also then 1, 2, or 3, that'll be fine, and you don't have to do the extra email. Okay, thank you, Rob. Appreciate that. And David as well. So when I do pass this around over here, just put 1, 2, or 3. If you change your mind between now and Tuesday, that's okay. Just let me know Tuesday, when you come in, and I'll give you the one that you want to take. So if you run into questions while you're studying, I will be answering emails. I always try to answer your emails. Sometimes it might take me a little bit to get to it, especially through the holidays, or through the Thanksgiving holiday this week, but I will be checking and I'll get back with you, okay? Any questions about retaking the test? If you retake test 1, it'll be just like test 1 before, and you will not use a calculator. So test 1, no calculator still yet, okay? Test 2 and 3, you can use a calculator. Each test is still the same material it was before. Yes, the questions will be slightly different, if whether the numbers are different or the wording, the word problems may be a little different, something like that, but it's the same material, okay? So you've got your old test to study by. That's probably your best thing to study. You've got the study problems I gave you when you were prepping for those tests, or the study guide I put on for test 3, okay? I am planning to post some sort of study guide for your final exam, okay? I don't have that on there yet. I'm also planning to post the key for the test I'm giving back today. Okay, I just didn't get it on before I came in this morning on your site, but it will be there. So maybe those will be of use as well for you. Okay, then on Thursday, December 4th, that'll pretty much be review. So that's when you need to come asking questions, any last minute concerns, right? Things you want to know before the final exam. And then on Tuesday, December 9th, that's when our class is scheduled by the ETSU final exam schedule. We're scheduled to take our final exam. And that timing is different, though. Remember, that is 1:20 to 3:20. Okay, so you can take the final exam here like usual in this classroom, over in Kingsport in that classroom, whichever room you want to be in, okay? So that's where we're doing the final. Any questions about that? So far, so good. All right, so well, I probably talked a little more than I meant to right there, but let me go ahead and pass back these tests, and we'll see if we have any questions on them real quick. So Cheyenne, bear with us just a minute here. Okay, Zach Silman, Tom Zaleski. Sorry for reaching Stephen Scheidler, Evan Riley, Aaron Mayer, Tom Ellsworth, Clay Humpkin, Brett Rathman, Sydney Lawson, Jamie Kinsler, Jacob Porter, Veronica Morlock, Jonathan Beck, Barry Moore, Gerald Rivers, Brendan Delgado, Chance Pritchett, Juan Gisbert, Rachel McCauley, Amy Spencer, okay, so overall the grades on these were much better than what we had before. Normally on this material the grades are a little bit better. I don't know, I think people like triangles better or something. There's something about that, they make more sense, right? So if there was anything bugging you about that test, anything you want to ask about, I'll give you a chance here to go ahead and ask. Anybody have something from there that you were really wondering about? I will be posting the key to where I work things out, but some things I want to mention to you about the test. First, never assume the triangle is a right triangle. Some of you made that assumption on several problems, okay? Even if you draw something and you're drawing it and it looks like a right triangle, remember, that's just your drawing, okay? Just like I say in here all the time, I'm not drawing things to scale. Neither are you. When you just freehand this stuff, we don't really know, you know. Are there ways to tell if something's a right triangle? Well, yes, like on the golf problem, for example, some of you took that to be a right triangle, but did you check and see if a squared plus b squared was equal to c squared, since you had those three sides on the golf problem? See, there's ways you can check, but you cannot assume that these things are right triangles. You can't even assume that any diagrams are drawn to scale unless they say so. So be careful about that sort of thing as well. What else was it I saw in here that I was going to mention? Oh, on the first one, the very first problem, we had this right triangle trigonometry. Just need to clarify a few things here. The angle that was up there, we had this and this, okay? Now this one is a right triangle because they're telling us it is, right? So that means we have sides A, B, and C, okay? And remember though that your hypotenuse is always the side that's the longest. It's across from the right angle. So here, across from the right angle, this one has to be the hypotenuse. I went ahead and labeled it C, but it's true that a squared plus 5 squared equals 6 squared. Some of you looked at that as though the 6 and the 5 were the legs and the missing side was the hypotenuse, and that's not the case on that, okay? So we had to find it this way. Another thing, whenever we're looking at this and we want to look at the sine of theta, in our right triangle trigonometry, we talk about the sine as the opposite over the hypotenuse. And in this triangle here, the opposite side from theta is side B, and the hypotenuse is side C. Now, when we first wrote these things down, I told you want to remember opposite over hypotenuse, not whatever letters we used that day. Some of you just went with those letters. Another thing I saw here is some of you were talking about unit circle trig, and you were using the sign was y over r, which made you go with a over c, right? Just looking at this. Problem with that is that where I've got theta right here, that's not what we could look at as a central angle without turning the triangle around. Remember, the unit circle trig went with the central angle that we were looking at. central angle being, one that has the vertex right there at the origin. So if we want to turn this one around and have it be the central angle, we're going to have to turn it something like this, to where if we're putting theta there, I've just taken that triangle and I've shifted it, okay, so that now, this is side C. That would be my 6 right there. And next to theta, the other adjoining side, or the side bordering theta, would be A, and here would be B is 5. So it is still supposedly, as you want to look at it there, or how you want to call it, y over r, but in this case it's still b over c whenever we adjust the angle to be the central angle. I wouldn't recommend doing this type of problem that way, but that's how we would think about it. Okay. So where I had theta up there, though, it's not, it's not positioned right now to be the central angle. Does that help a little bit for some of you on seeing the difference there and looking at that? They do all fit together. Unit circle trig, right triangle trig, it all does work together. But we've got to be careful about our angle placement here and where our sides are in relation to that. Anything else about number 1? I didn't work out the problem, but if anybody wants us to go further with that, we can certainly do that. Okay. Any questions you've seen from the test? Yes. Can you go over the bonus question? Yes, we can do the bonus question, sure. And this time, I feel like I was a little more generous on the bonus. I let it count 10 points, which that boosted some of your grades as well if you got that correct. However, you had to work hard for those 10 points. There weren't many points given between like 5 and 10. You might get 1 for drawing the picture correctly, but nothing else. You might get 2 for starting it right, something like that. So it was a little bit, just more on the lower end if you didn't get it all the way worked out. So on the bonus, we had this. A ladder leans against a building that has a wall slanting away from the ladder at an angle of 96 degrees with the ground. So here's the ground. I have a building, but on my building, my wall, whoops, that's a little bit slanty, but it's slanting away from the ladder. There's my ladder. Remember, the building slanting away at an angle of 96 degrees with the ground. This building is not perpendicular to the ground like the other ones that we have looked at, okay? This building's not perpendicular to the ground. So we have to look at it a little differently. It's not a right triangle. There's no right angle in this. Definitely, if we have a 96-degree angle, we cannot have a 90-degree angle, can we? No, there's no way, because they would add up to 186 now, and we're larger than the triangle should be. So we've got to look at it, it's just a triangle with a 96-degree angle here. Some of you drew some really good pictures, by the way, so I like good pictures. But ladder leans against a building. Okay, it has a wall slanting away from the ladder, an angle of 96 degrees with the ground. If the bottom of the ladder is 23 feet from the base of the wall, and it reaches a point 52 feet up the wall, then the question was, how tall is the ladder to the nearest foot? So we know here, we know 2 sides and the angle in between them, the angle that's enclosed by those 2 sides. That's side angle side that we looked at before. With those types of triangles, we don't know an angle on the side across from it, and we don't know that there's a right angle. So we resort to the law of cosines on this one. And we're looking for the length of the ladder, which I don't know, what do you want to call that? What letter? Maybe C. It's not a right triangle, but you can call it C, you can call it L, you can call it whatever you want to. In fact, let's call it X instead. I think I like X better. Okay, but the formula you're going to use with the law of cosines looked like this. C squared equals A squared plus B squared minus 2AB cosine of angle C. And remember, the law of cosines is used when we know 2 sides and an angle in between those 2 sides. So we're going to take then X is what we're looking for. X squared equals the other two sides squared minus 2 times those other two sides times the cosine of 96 degrees. So when you work that out, I really don't know what you get when you work that out, but whatever you get, x is going to be the square root of all that. Let me see if we've got this here. So my advice is always to wait and use your calculator, at the end. Well, what you could do here is you could use your calculator on this step right here and put in all that 52 squared plus 23 squared and so on. Total that up, in other words, equal it out, and then take the square root of your answer. Okay, so that would work right there to get the answer. There were a couple of you who put this down correctly, but somehow when you put it in your calculator, you got something else. I think there were 2 of you who had worked it out pretty much correctly. I mean, it was correct until at that very end part. We ended up with x is approximately equal to 59.017, I think, something like that. And it said to the nearest degree, so that's about 59 feet. Now, I do realize that a few of you got 57 feet for your answer, and you're saying, I was just 2 off. Well, if you bring me that short ladder, though, 57 feet, it's not going to reach where I wanted it to on that building at that angle. That would be a problem. Also, the way you got 57 was not by using the law of cosines. If you got 57, I'm pretty sure the way you did it was you used the Pythagorean theorem and did a squared plus b squared equals c squared, which will not work on this one. Okay, again, it's not a right triangle. So I tried to look for things, and see what you were doing with it and that sort of thing. Any questions there? Any questions on punching that in your calculator? Why did that not work out right when you punched that in before? I think yours was 1, Steve. Oh, yours was a different question?
Mine was 6, where I did that. I don't know. I have issues with my calculator sometimes. I'll type in it 3 times in a row, and I'll get one answer, and then the 4th time I'll get a different answer.
Okay. So that's not what happened with yours then? But the question was the same, is that correct? Or not? Or did you tell?
6 was that one that I typed in.
Oh, 6 was the one that didn't work out. Okay, I was thinking it was on the bonus for some reason. I knew it was a law of cosines problem there, right? And it wasn't just you. There was somebody else in here that happened. Yeah, I was thinking it was you over there. And it was number 6 also. Yeah, because I knew it was the same problem. Okay, so any questions? Any other questions about that? About the test? Yeah, go ahead. Number 4, sure. Let's look at 4. It's like the longest problem on the test. All right, 2 sides and an angle are given. Determine whether it results in 0, 1, or 2 triangles. All right, A is 23, B is 18, angle B is 15 degrees. Okay. The way we were looking at this was, well, first we were drawing just a triangle in general. And we've got side A is 23, B is 18, angle B is 15 degrees. Okay. And it's law of sines. We know an angle and the side across from it. And so we started out with law of sines, the sine of 15 degrees over the side 18. Okay, we're not doing the sine of 18, we're just doing that side measurement, is equal to, and we have to work with angle A over side A. Okay, so we work this out. 18 sine A equals 23 sine 15 degrees. And then we'll have to divide by 18 so that the sine of A is equal to 23 sine 15 degrees over 18. Again, there were a few of you who wanted to, way up at the beginning, go ahead and do sine of 15 degrees on your calculator. Don't do that. It causes round-off error. We've talked about round-off error a little bit in here. Wait till the end to type it in. It saves you time, too. You're not punching that calculator every minute, right? So wait till the end when you know exactly what you need to put in there. We don't need to know before now what the sine of 15 degrees is. So A is going to equal then the inverse sine of 23 sine 15 degrees over 18. And that turned out to be, I didn't bring my key today, but let's see, I think we've got it right here. That turned out to be 19.31 degrees, right? Okay, so 19.31. That's definitely then illustrating that we're going to have one triangle at least. We might have two. How did we find out? We look at the supplement of that angle, 180 minus 19.31. This is how we talked about, and said, could angle A equal that supplement, because the sines of the two angles are the same, making that proportion, you know, when we do the sine of angle A over 23, we'll get the sine of 19.31 degrees over 23 is going to be the same ratio as the sine of the supplement of the angle over 23 degrees. So when we did 180 minus 19.31, we got 160.69 degrees. And the question was, could angle A equal that if this stuff up here was still true? Can that happen? And the answer is yes, because angle B just had to be 15 degrees. If we put the 15 degree angle B with the angle A that we're proposing is 160.69 degrees, that just gives us 175.69 degrees. And so we still have, even though it's a small angle, we have enough space to put a third angle in that triangle. Okay, so we say yes, that's going to work out. So that's why we know there's going to be two triangles. So I'll label this was my first A over there. Now I'm at my second A over here. But I can only work with one triangle at a time. So I'm going to go back to triangle 1 here for a minute. A up here was 19.31 degrees on the first one. So now I would set up, well, first I would probably go ahead and get angle C. To get angle C, I'm going to take 180 minus the 19.31 plus the 15 degrees. So 180 minus 34.31 degrees. And that's going to give me 145.69 degrees. That's what I'm going to get there. Okay. Last, I have to find side C for that one. So I'll have to resort back to the law of sines now. I cannot use right triangle trig. It's not a right triangle again. But I can go back and say the sine of 15 degrees over 18 is equal to now the sine of 145.69 degrees over side C. And do the cross multiplication. So I've got C times the sine of 15 degrees equals 18 sine 145.69 degrees. Divide by the sine of 15 degrees to get that part out of there. When we divide, we do not subtract the angle values. Some people are looking at subtracting those, doing a little bit different operation. But 18 times the sine of 145.69 degrees divided by the sine of 15 degrees was equal to 39.2. So that was all the first triangle. And then we do the same thing over here where we're going to work with the second triangle. So I could draw another triangle if I want. You had a really good drawing, Jonathan, showing how the triangle was inside. A couple more drew that way. I just remember definitely seeing it on yours, not to put you on the spot there. But what's happening is, and I don't think I can draw it really well up here. I'm not leaving myself enough space. What's happening here is angle B has to stay that 15 degrees. So I think, like, did you put B over here for 15 degrees? But then we've got some extra part down here being formed where we're forming two triangles where one of them has an obtuse angle and the other one has the acute angle. But in one triangle, this is side B, in my triangle on the left, but in the other one, this is side B. So with my triangle with my obtuse angle, triangle 2, so that would be, I can't write it in there, there's not enough space, but B2 is going to be that side coming down in the middle there, and B1 is over here looking at it that way. And so then we placed our other angles. Let's see, you put C. Where did you put C on yours? I'm just trying to think here how you had yours. Yeah, okay. So C was up top, and for the first triangle, that's the whole thing, right? That's how you had it for the first triangle because we're looking at that. And then A is down here when we're looking at A for the big triangle, but for the small triangle, A is this little angle right there, right, for the second one. That's the obtuse. That's the 160.69 degrees. So drawing it in on mine, it looks a little stranger, and that makes this side A for the second triangle. And am I looking at that right? This is side A for the first triangle. When I'm trying to draw it in here, I'm looking at what's going on here. But anyway, that's not how we drew it up in class. That does work out very well for that one, for all those where there's two triangles. Some of you saw that there was two, but you weren't sure how to get the second one. And several of you said there was just the one, which you did get correct on that one. But let's go back and finish solving this second one out just to make sure we've got that here. And I'm going to pull it out over here and look at it. Again, my drawings are not to scale. Neither were yours. Okay. This is triangle 2 here. We know A still has to be 23, B still has to be 18. So actually, this is my, yeah, that should not have been A2 down there. This is A equals 23 right here, because that one was set, right? That one was set when I look back over here. All right, so we have the sine of 15 degrees over 18 is equal to the sine of, well, what are we going to work with now? Oh, we had to find angle C first. I guess we should do that. Let me pull this part down a little. Well, okay, I can do it with this thing. There we go. And leave a little space, because first we should have found angle C after having found angle A, and we already know B. We know that A and B add together to give us 175.69 degrees, making angle C be, what was that one? 4.31. That's when we said it was going to be really small. So 4.31 degrees for the second one. And then side C over here, now we can find side C, the sine of 4.31 degrees over side C. And that's going to give us C sine 15 degrees equals 18 sine 4.31 degrees. And C is equal to 18 sine 4.31 degrees over the sine of 15 degrees. So this was C for the second triangle. I believe it was 5.23 there, okay? Without using my calculator up here, I'm using someone else's paper here, okay? Yeah, Jamie.
You said that the way you can tell if there's two triangles is if like the 19.31 degrees, or the sine of 19.31 and the sine of 160.69 are equal to each other.
Were they not equal?
They are.
Yeah.
I just wanted to make sure that was right, because
well, they're always going to be equal, because what's happening here is they're supplements of each other. That I was looking, maybe we didn't subtract correctly here, but what we're doing to actually find out what that other angle might be is we are finding the supplement of the first angle that we do find. So the angle we found first was 19.31. We didn't have a choice about which angle to find first. It had to be that angle A because of the information we were given. So whatever we find for that, that designates that's going to be part of one triangle, but then subtract that value from 180 and see if that value you get will work as well with the angle you were given to begin with. Will work, meaning you got to have three angles in the triangle adding up to 180. So if, when we got that 160.69, when we added that to the angle we were given, the 15, those two together still have to be less than 180 degrees in order for there to be a second triangle. If they're more than 180 degrees, then we can't have a third angle, right? And we're we're not forming a triangle there. But as long as they're less than 180 degrees, it works. And yes, the supplements have the same sine value.
Okay.
So that puts them back in that ratio, the same for the law of sines. Okay. Anything else on this one before we leave it here? And number 2, we have tangent 65 degrees. There were actually several ways to look at this. Some of you came up with some other ways that were equally correct, but here's how I was looking at it. Anyway, we went with it. We were supposed to be, well, it said you don't need to use a calculator, which tells you, I didn't intend for you to just plug this in your calculator. I wanted to see some knowledge of the theorem of the complementary angle theorem that says cofunctions of complementary angles are equal. We had talked about problems like this before, and we talked about, showing your work for this. So here's what we would do with this one, or here's one way you could go with this. Tangent 65 degrees minus, since I have tangent 65 degrees and I see 65 and 25 are complementary angles over here, so I can rewrite this top one so that it's the cofunction of the complementary angle, making it equal to what I already have there. The cofunction is sine. The complementary angle is 65 degrees. Down here I'm leaving this one alone because it's already in terms of 65 degrees. I'm trying to get everything on mine in 65 degrees. Okay, there were a couple other ways you could work with this, and some of you did, and I read through it. It was good. Okay, and then there were some ways you all tried to work with it that was not so good, but I tried to make you a note if that was the case as well. But that gave us then the tangent of 65 degrees minus, and the sine over the cosine is the tangent, and the angle 65 degrees, and that's equal to 0. Okay, so yes, the answer was 0, but yes, I was interested in how you got there. Okay, how you got that 0 there. Tom? I'll do 7, and then we're moving on, okay? So let's do 7, and then if you all have other questions individually, you can ask me about them through email or after class, okay? A radio transmission tower is 120 feet tall. This is exactly like one that we had on the study guide, by the way. How long should a guy wire be if it is to be attached 10 feet from the top? So we're attaching it 10 feet down here from the top. It's a wire out here. How long should the wire be? That's what we don't know. It's attached 10 feet from the top, and it's making an angle of 21 degrees with the ground. 21 degrees is the angle made with the ground. Okay, got that part right. Give your answer to the nearest tenth of a foot. That's supposed to be an X. It kind of looked like a T, didn't it? I guess we'll do it that way. Is that better? I don't know. All right, so here we are saying we've got a tower and we've got a ground, and we talked about those problems. We can say, safely say, unless we're told that the tower's leaning, we can safely say that's a right triangle, and we want to know the length of the wire. So what trig function can we use here?
Law of sines.
Well, you can use law of sines. What about right triangle trig? We could use just the sine. The sine of 21 degrees equals the opposite. Oops, it's not 120 though now. What is it?
It's 110.
Yeah, this is 110, right. So the opposite over the hypotenuse. You could use the law of sines if you did. Let's see, what are you going to say there? The sine of 21 degrees over 110 is equal to the sine of 90 degrees over x, right? That's what you'd be using for law of sines. So either one works here. If you use the right triangle trig, we're multiplying by x, we get x sine 21 degrees equals 110. And x then will equal 110 divided by the sine of 21 degrees. Over here we have, doing it with the law of sines, we got x sine 21 degrees equals 110 sine of 90 degrees. But we happen to know that the sine of 90 degrees from way back on our unit circle was what? 1. So we have x equals 110 divided by the sine of 21 degrees. Either way, we're getting x is equal to what? On this one, 306.947. But it said to round to the nearest tenth of a foot, so it'd be 306.9 feet. Okay, that's what we were looking at there. Alrighty. Well, hold on to those then, and I just noticed I forgot to send around the attendance sheet, so let me start there. Remember, put 1, 2, or 3 if you're planning to retake the test. Now, let's look back in Chapter 14 just a little bit to finish up some of our limit information. So I do want to go back toward the limit part just a little bit there to kind of clarify a few things in a little bit of the time we have left. So in doing so, I am going to pull out this last problem from the test still yet, where we had the limit as x approaches 2 of the function, and it looked something like this. So this one did something like this, okay? So we had that function graphed. This was 10a back on the test also, but the limit as x approaches 2. Now what we had looked at before the test about limits was we are looking basically for the behavior of the function when we talk about the limit. We're looking at what's happening with the y values as the x's are getting closer or approaching a particular value. So as the x's are coming in closer to 2, from both directions, from the left and the right of 2, what's happening with the y's? Well, as the x's are getting close to 2, the y's are also getting close to this 2 up here. Yes, there's no value there. We see that. There's no point value there. The function value at 2 is that 1, where the point 21 is, but the limit here is equal to 2 because as we get closer with the x's, as we come in closer and closer to 2 from the left or from the right, the y's are also approaching where that open circle is. You see that on your graph? Yes, go ahead.
Does the open circle mean that that point is not inclusive for the equality? Or
right. It means that point is not actually there. This curve or whatever it is up there that we have graphed mostly around that point is not actually going through that particular value. It's not going through the 0.22. It's kind of, there's a jump there. It goes up to it and then it jumps and goes on. And we illustrate that with that little open circle at that point. The actual point is at 2, 1. It's still considered a function though, because no matter where we put a vertical line, it's only going to cross through the graph once, including if we put that vertical line through x equals 2. It's going through the 0.21. Yes, it'll go over that open circle, but that's not included. Okay, but that's how we illustrate. Around the point, yeah, everywhere except where x equals 2, this function is continuous, but it is discontinuous when x is equal to 2. Does that make sense there? So when we come up here, let me come over here to the graph just a moment. But when we come up here and we're following this, you know, normally we would like to see it just be continuous and go on. And likewise, if it were continuous and going on, then the limit as x approaches 2 would still be at 2. But in this case here, even though there's no point there, as our x's are approaching 2 from the left, our y's are getting closer and closer to 2 up here. You know, like we're here first, then we're there. We're getting close to that 2 value. We're talking about the behavior of the function, not exactly where the point lands, but what's this function doing? As the x's approach 2, the y's are approaching 2. As the x's approach 2 from the right, the y's are approaching 2. So we say the limit of the function as x approaches 2 is equal to 2. However, the function value at 2 is 1. Okay, so f of 2 is equal to 1, but the limit as x approaches 2 is equal to 2. And we'll look at a few more like that and maybe help see it besides this one, okay?
Okay, but that's different than like it being equal, like as it approaches 2, is it wouldn't be equal to, or the limit wouldn't be like 1.999 since
Right.
since it doesn't include the point.
Right. The limit is just saying what value is it approaching. So we go ahead and say 2 on that one. Right. Even though the function value will not be 2. I know that's a little bit kind of crazy there, I guess, but a little tricky. We'll look back at another one like that. Another thing I want to say about this particular type of problem is when you give the answer here is just 2. It's not f of 2. It's not x with an arrow pointing to a 2. So be careful about how you answer these. Just to give a little bit of a preview here, like we say, for those of you going on into calculus. Part B on that one said the limit as x approaches pi halves of sine x minus 3. And on this one, you were not asked to graph, but you could have graphed, and a few of you did. If you did graph, let's see, we had sine is 2 pi periodic. We're wanting to know what's happening as x approaches pi halves. But this is the sine graph dropped down vertically 3 units. So normally we start the sine graph at the origin and come up and have it cross down through the x-axis at pi and then come back up to 2 pi. So now we would start down here. It's still got an amplitude of 1. So it's going to do something like, I've got mine kind of maybe drawn out too much. Something like this is how it's going to be going on my sketch. My sketch is pretty bad, but we can see, I think, from the sketch, so that if I start here, that it's coming up to 2 pi before I repeat again, okay, on my sketchy sketch, I guess we could say. As the x's approach pi halves from the left and from the right, this is continuous. This is a continuous wave here. And it appears that the y's are approaching what?
Pi halves. Oh, wait, the y's?
The x's are approaching pi halves. The y's?
Negative 2.
Right, negative 2. And this is actually supposed to probably be on up a little bit because it actually goes through the point pi halves negative 2 in this case. We can also see that by plugging in pi halves into the function here that we are using, sine pi halves minus 3. Sine pi halves is 1 minus 3 is negative 2. It's the limit of negative 2, but the limit of the constant is the constant itself. Okay, so we get negative 2 for that one. Either way we look at that. So let's look at a graph here that's in the textbook for a minute. It's over on page 883. If you have your textbook there, I can put it up on the screen here for us. So let's do that a minute. We're going to look just a little bit more at approaching from the left and from the right and see what we can do with that. Well, let's put it about right there, except y'all got my answers up there too for the textbook, right? That's okay. That's okay though. So if we're looking at this one, approaching from the left and from the right, let me pull my microphone over here. I forgot to attach today. Okay, so there's a lot of questions about this graph, but you can see that, you know, it starts, the x's, we have x values from negative 8 up to negative 6, but we don't actually have a value at negative 6. We have a vertical asymptote instead. And then we go from negative 6 up to, where's the next place we don't have a value? 4. We don't have any x value being in the domain at 4. And then it goes on out to 6. So that's our domain. And our range appears to be going, though, all the way down to negative infinity and up to infinity as well there when we look at that. Now, what I wanted us to look at, though, a little bit here was the limits themselves. So let's just see if we can kind of see what's going on here. What would the limit be of this function as x approaches -6 from the left? Can we look at that and see?
It'd be infinity, wouldn't it?
It would be infinity, okay? You are seeing that there? I'm trying to see if I have a place to hook this. I don't know. All right, so as we approach -6 from the left, the graph is continuing on to infinity. This at -6, x equals -6 is a dashed vertical asymptote there, so we're not crossing over that vertical asymptote. As we approach -6 from the right, where's the y's going to? Negative infinity, down this way, okay? Which means that if I just ask the question, what's the limit as x approaches 6, what is that going to be for this function?
Infinity?
They have to be the same from both directions in order for the limit to exist. So, let me go over here just a moment. This was off of page 883. We're approaching -6 from the left of the function and approaching -6 from the right of the function. And when we approached from the left, it was infinity, and from the right, it was negative infinity, right? When we looked at that, without the picture up there, it's harder to see. But when we approach from the left and from the right, we're getting different values, which means that the limit as x approaches -6 at all for that function just does not exist, okay? It does not exist because the limits approaching from the left and approaching from the right are not the same values. In order for the limit to exist, we have to be converging into the same value, whatever it is. Either they both have to be going to infinity from both sides of that, or both to negative infinity. But if one's going up from one direction and going down from the other, then the limit itself is not going to exist. Let's look at another one from that graph there, okay? Let me pull the graph back up here just a minute. Okay, this time we'll look at the limit as x approaches 0 from the left. The limit as x approaches 0 from the left is what? As x approaches 0 from the left, what's happening to the y's?
It's getting closer to 3.
Okay, the y's are getting close to 3. That's at 3 because there's 2, there's 3, there's 4. So it's 3 as x approaches 0 from the left. The y's are getting close to 3 as x approaches 0 from the right. What's that one? 3 also. So the limit as x approaches 0 is 3 because from the left and the right, it's the same. Okay, are we seeing the difference there in those two? Any questions so far? What about the limit as x approaches -4 from the left? There's -4. As we approach -4 from the left, it would be 2 because as our x's are getting close to -4 from the left, let's suppose my x is here, my y's there. My x is here, my y's there, right? Okay, so it's going up on that until we're getting up close to that 2 right there. As the x's approach -4 from the right, what's the limit this time? It's at -2, even though we've got that open circle there. That's the value that the values for y are approaching, -2. So the limit as x approaches -4 for this function is, it does not exist, right? What about the limit as x approaches 4 from the left? It's 0. As x approaches 4 from the left, the y's are getting close to 0. As x approaches 4 from the right, 0. So the limit as x approaches 4 for this function is 0. Is that helping at all, looking at that one? Okay, a little bit there. So the idea is the limit only exists if the values for the limit are the same as we approach whatever value x is approaching from the left and the right, the values must be the same. Okay. So I thought this was a good graph at least to look at to see for that. Any questions there about that one? Okay.
So there's like no special math involved in that. I was just looking on the test.
Yeah, there's no special math involved in that for this right here. We're just looking at the graph right now to look and see what the limit is. Now, we do have some where we have some math involved, so let's look at one of those, okay, just to kind of clarify also. So let's go over here to, this is off of page 877. You all have worked with some of the problems from back here. I asked you to sometime before the test time, but let's look back and see just a minute what we have here. This is number 13. It says the limit as x approaches 2 of 5x to the 4th. Okay. And basically we're using algebra here to find these limits, although you could graph them if you want to look at them graphically. That would work. But this one, what we can do is just plug in the value there. So the limit as x approaches 2 of, when we plug in that value, we're going to get 5 times 16, which is 80. So it looks like we're getting 80 for that one. So actually, looking at that one, we're kind of glad that we didn't have to graph it and look at it, because the y's were getting close to 80. If you know what I mean, that's not fun to graph, at least by hand. So this is just involving algebraic substitution to get that limit right there. And we did mention, you know, we would originally try to just plug the value in and see if it worked in the function to give us a value. So we have some rules for that. Overall, we've already mentioned the limit of a constant is a constant. Okay, the limit of a constant is the constant. What's a constant anyway? What's a constant?
Oh, like the 5 and the 5x to the 4th power would be the constant.
Okay, so if it just said 5, that would be a constant. The 5 with the x to the 4th power, that 5 is called a coefficient. Okay, it's the coefficient of the variable there. But the constant, or a constant, is when we just have a number with no variable. So I'm going to give you a little bit of an English lesson right here with the vocabulary. Okay, what does the word constant mean? Okay, continuous, I heard, or if something is constant, it
Is always the same.
is always the same, right? So a number value that is always the same is something like 5, 2, just a number. What does the word variable mean? What root word do you see on the word variable?
Vary.
Vary, what does vary mean?
It changes.
It changes. How does it change? Well, it depends on what the value of the variable is, right? So if I have something like 5x, that's not a constant anymore because of that variable. That value would depend on what I plug in for that variable there. So we're having a little bit of English vocabulary and math today. But constant, they don't change. So it's just a numerical value with no variable. And if there's a variable, you know, that's what causes change on those. All right, so we're going to look here on this rule. The constant function is f of x equals b, some value b. And all this really means then for us is the limit as x approaches whatever number you want it to approach. I'm going to say x approaches 2 of 7 is equal to just 7. The limit of a constant is that constant. We might have looked at the graph for this last week. I can't remember if we did or didn't. But, you know, this part right here is always our f of x part. So that means that f of x is equal to 7 here, or we're looking at the graph of y equals 7, in other words. It's a horizontal line going through 7 on the y-axis if you have y equals 7. And if we're looking for the limit, you know, since we've been looking at graphs a little bit here, the limit as the x's approach 2, we want to know what's happening with the y's. Well, the y values on this one are always going to be at 7 because, you know, that's that graph, that horizontal line going through 7. So that's why we say, you know, the limit of the constant is just going to be the constant that we are using there, no matter what x is approaching. It doesn't matter what x is approaching, okay? So then we can just plug in the values, though. If it has a variable in there, we can plug in the values. And it's also true that the limit of a sum, if we have the limit of something plus something, then we could do those separately and say it's the limit of the first part plus the limit of the second part. And I know you're not going to like to hear me say this, but the limit of a sum is the sum of the limits. That's what that means, okay? Let's write that out here. Okay. If I have the limit as x approaches c, and it's of f of x plus g of x. So I've got two parts here, whatever I'm working with, a sum of something. The limit of a sum is the sum of the two limits. So we can break them up, in other words. The same goes for if it's a difference, the limit of a difference, the limit of a product, the limit of a quotient. We can separate those things. So I could say, you know, if it said minus in there, I can just do the difference of the two individual limits. If it's said to multiply, so maybe we have like this, f of x times g of x. I should stick with brackets, I guess, there. So the limit of a product is the product of the two limits. And likewise, the limit of a quotient, meaning we're dividing f of x by g of x, is equal to the quotient of the two limits. Okay. So what does that mean for us? Some of you are still writing, so I'm holding up just a minute here. Then I'll put an example up here. I'm going to use one from the textbook here. We actually just did a limit of a product when we did that 5x to the fourth. That's 5 times x to the fourth. So I want to go back to that one for just a minute first and show our rules in place here. This was the same as, and we didn't have to break this up to do it, but the same as the limit as x approaches 2 of 5 times the limit as x approaches 2 of x to the fourth. See what we're saying there? It's the limit of a product is the same as the product of the two separate limits. The limit as x approaches 2 of 5 is what? 5, because that's the limit of a constant is a constant. Times, here we actually plug the value in, 2 to the fourth. That's what we did up there anyway. So these rules are there. We know what they're saying, but you know, this has given us the rules to justify it. Okay. Nothing's really changed from what we looked at before. We're still plugging in values. Okay, we're plugging in values to work with these algebraically on this part. Let me give you one more to try here. Okay. Let's go over here. We'll do I think we did some of these already, but how about this number 10? The limit as x approaches -3 of x on page 877. What's that one going to be?
It'd be -3.
Yeah, that's just -3. Sometimes though people look at that and say, what? Yeah. If you feel like you need to still practice some of these, look on page 877. You can try 7 to 23 odd. And then if you want to look at that graph a little bit more over on page 883, look back at numbers 19 through 25 on that part, okay, and see what you can see. All right, so meantime, you all have let me know what test you want to retake, right? And that's what's coming up next. If anybody has any questions about their test or their grade, please do let me know. David, do you have a question? Yes.
Yeah, the other two students that didn't come today, you're going to get over them and tell them that they don't need to show up on Tuesday unless they're going to take a makeup.
I'm going to send out an email so that anybody who did miss today will kind of know the game plan there. So I'll get an email sent out here to the class, okay? And so they'll know. All right, and I'll get some things over to you on that.
Interesting side note on your bonus question on the test. Where I come from, when we talk about a ladder being tall, we use a value of how far off the ground one end is.
How far off the ground?
How far off the ground, yeah. When we say how long the ladder is, we mean how far it's stretched out, like what you wanted. But when we say how tall is the ladder, we say, well, it's 56 foot up on the wall, so it's 56 foot.
Oh, I see what you're saying.
Yeah, we would never say tall. Yeah.
Yeah, that's how that one was phrased. I don't know why. So where are you from?
The Appalachians, West Virginia.
Oh, okay. Well, that's all right. Did you get your truck back?
Yeah, I got the truck back, but my wife's car is broke down now.
Oh, no. Okay. Well, good luck to you. Have a good Thanksgiving, everybody. Okay.
Thank you, you too.
You're welcome.